Good morning. Thank you so much for the invitation to speak. I'm really honored that you invited me. I hope I can share some valuable insights with you this morning on both mining and comprehension. And so I sort of created this tongue twister of a title for you, Mining the Mind, Grand Challenges in Comprehension and Mining. And I want to help deconstruct that for you over the next 35 minutes or so. So my talk today is going to be about this word, interdisciplinarity. This is just drawing upon two or more branches of knowledge to try to understand the world and the phenomenon. Interdisciplinarity is both what this talk is about, because I'm trying to bridge these two worlds of comprehension and mining, but it's also about interdisciplinary research in my experience as a researcher. This is something that's defined really the research that I've done over my career. So for those of you who don't know me, I'm an associate professor at the University of Washington Information School in Seattle, Washington. I have a background that is interdisciplinary. I studied computer science, psychology, design, and learning, all relatively equally. I've been programming for decades. I study and invent interactions with code, and I theorize about what programming is, and I try to do that from all of these different perspectives. And really, I do work at all of the boundaries between these different disciplines, just studying programming constantly throughout all of these different perspectives. So there are really four periods of my career so far, and each of them has been interdisciplinary in its own way. When I was an undergraduate doing research with Margaret Burnett at Oregon State, I studied end user programmers and spreadsheets and really wondered, how do we help end users test effectively without any testing skills? This was research that was both technical in that we were thinking about things like test coverage, but it was also human in that we were thinking about people without any training in software engineering trying to be effective at testing. I went off to graduate school after this and worked with Brad Myers at Carnegie Mellon and asked this question: how can we make debugging easier? And how can we make it faster using methods from human-computer interaction, methods like studying people and their problems before designing tools and technologies? And this resulted in some of my dissertation work on the Y line. And this won Most Influential Paper Award at ICSE this year. So I'll be presenting a talk at the closing plenary on this Friday. So I hope you'll come to that. And then after graduate school, I went off to join the faculty at the University of Washington at the Information School. For those of you who don't know, information schools study the intersection of people, information, and technology. So this was a perfect interdisciplinary fit for the kind of work that I do. I also spent 4 years at AnswerDash, a startup that I co-founded that's still running. And here, as faculty, new faculty, I was trying to understand, how can we understand field failures at scale? All of the bugs that are happening in practice and all of the consequences that they cause to people in their experiences. I wanted to understand how to make that kind of bug triage that companies have to do evidence-based, so they could use data to make these decisions instead of their instincts. And I went from there and came back from AnswerDash, my startup, where I disseminated a lot of the work that I'd done in my lab, really with this interesting new perspective on what it meant to be a software engineer and what it meant to be a great software engineer. And I started new research on making better software by making better developers. So thinking about ways of helping developers learn more rapidly, both programming languages and APIs and learning at scale, but also studying software engineering expertise. And so throughout all of this time, I've had a lot of exposure to comprehension and mining. One of the first conferences I went to was the International Conference on Program Comprehension, which was a workshop at the time. This was back in 2003 in Portland, Oregon. I've also mined software repositories for a long time, since 2005, when I downloaded my first dump of the Linux and Apache and Firefox bug repositories to do some analyses on them. But I haven't attended ICPC for 15 years. And I haven't really ever attended Mining Software Repositories. And so in some ways, I'm an outsider to these two communities. And so it's a really unique opportunity for me to reflect as an outsider and show you how I see you work, but also talk about some of the interdisciplinary opportunities for advancing both of these areas. So I've talked a lot about me. Let's talk a little bit about you. Who here regularly attends ICPC? Okay. And who here regularly attends Mining Software Repositories? All right. Now, here's the interesting question. Who here regularly attends both of these conferences? All right, and as we can see, there's not a lot of overlap here, just a few people, and I think I probably know all of you who've raised your hands. So this is the opportunity for this talk, is to do the bridging that needs to be done between these communities. The people who had their hands up for both of these are really key to building this bridge. I think my role here is to try to show you what this bridge looks like so that you can figure out what those connections might be, and I can empower you to try to build it. So I'll really focus on three things in my talk. One is how I see the two communities of mining software repositories and program comprehension and the work that we're doing in these two fields. Second, I want to talk about 4 missed opportunities at the intersection of these two fields. And then I'll conclude with some ideas for next steps about how to do some of this bridge building. Before I get started, just one quick disclaimer. In attempting to build a bridge between these communities, I'm going to identify some weaknesses in each community. I don't want you to take it personally. My work has the same weaknesses. Really, I'm just trying to be self-critical and critical of our own communities to try to find opportunities to improve. This is what we all should be doing as scientists. Everyone here really is doing great work, but to make it greater, we really just have to surface some of these shortcomings so that we can act upon them. So let's start by building some common ground about the phenomena that we're all trying to change. Programming. This picture of a hackathon really does have it all. It shows the beautiful, complex, messy activity that can be anything from wildly creative to formal and precise. It shows individuals reasoning about code but coordinating their work. It shows the hidden traces of activity being captured in IDEs, version control systems, and issue trackers that we might use to understand what's happening on this team. All of us in this room want to make situations like these better, and by extension, software better. And so what we have in common here really is that we want to make programming and software engineering more effective and more efficient, more enjoyable, more successful. All of us want to do this through rigorous discovery of new tools, processes, insights. We really only differ in how we go about doing this research. These are the methods that we differ in, and what we believe will make a difference, the phenomena that we're actually trying to study and intervene to change. And so let's talk about some of those differences between these communities. On the program comprehension side, the phenomena we think make a difference are the developers themselves. We tend to study perception, cognition, decisions, collaboration, the contexts in which decisions are being made. This is all about what's in people's minds and the context around them. Even when we're making program comprehension tools, we're focused on changing what's happening in the developer's mind for the better so that they can make better decisions. The result of a lot of this work on comprehension is new science on how it is that people comprehend programs, new tools that support a developer's program comprehension, new evaluations of strengths and weaknesses of tools. Now, all of this is in contrast to mining, which focuses on very different phenomena. The units of analysis here are things like code, commits, issues, dependencies, defects. Now, from a mining perspective, this is all about traces of the activities that are residual from all of the behavior on the team, and how we can learn from these traces, the methods that we can use to learn from them. And the result of all of his work is very different stuff from comprehension, right? New science about the process of software engineering, methods, architecture, domain, defects, technical debt, techniques for making predictions about all of these things, and new methods for analyzing all of these things. So these really are two sides of the same phenomenon, right? Comprehension on the left, thinking about developers, and mining on the right, thinking about the traces of their activity. And yet, despite the differences in these units of analysis, both communities really are studying the same phenomena. They're just different lenses on programming. One's a human perspective, one's a data perspective. And the focus on each of these, is actually productive. So with comprehension, we get better decisions, right? We get tools that optimize to enhance comprehension. We get processes that optimize to streamline our collaboration. We get descriptive and predictive theories of comprehension that support design and the learning of software engineering. But when we focus on mining, what we get is better modeling, better predictions, better models of software process, better tools for software analytics. All of these things really help us understand at a larger scale how it is that software engineers engineer software. And this disciplinary focus of each of these different lenses is actually very productive. When we focus on comprehension, we get a sort of enhanced developer understanding of complex systems. And when we focus on mining, we can enhance developers' processes. Neither of these are really need to be interdisciplinary in any way. By focusing, we can actually get really valuable contributions out of them. Now, the downside of this, of course, is that there are missed opportunities around connecting these two phenomena that are inherently about the same thing. So I see 4 missed interdisciplinary opportunities, and I want to talk about each of them in turn, and then we'll take a step back and talk about next steps. All right, so the first one is what I'm going to call mining the mind, trying to understand what's happening in a developer's head. And doing that in a way that's rigorous and scalable for the kind of complexity we care about. Now, the problem I notice here in the literature in program comprehension is that many of our studies are small sample lab studies. I took a look at the preprints for this year's proceedings in ICPC, and of 16 preprints this year, 6 include studies with human subjects. First of all, that's not that high. I would have expected it to be more. They recruited between 8 and 88 participants. They were all short tasks, interviews, surveys. I use all of these methods myself. There's nothing wrong with them per se, but many of these studies really need longitudinal, ecologically valid context to strongly support their claims. These lab studies just are not enough to help us establish a rigorous understanding of what happens when people are comprehending code. So all of these really rich results can result in a lot of great stuff. So here's one paper on just-in-time feedback, what experienced developers like about static analysis. This is a really interesting and solid interview study of 29 Smalltalk developers about a static analysis tool. It was really great for understanding developers' sentiments about the tool. We learned a lot about what they do and don't like about the tool, but it's not great for understanding the impact of the tool in practice. It relied on retrospective self-report. Developers had to say what they liked based on their memories. This is not great data about whether or not the tools were actually effective in practice. They may have misremembered or sort of fabricated things because they didn't have a memory of what their experience was. Now, the solution here, if we think about this from a mining perspective, is to try to measure comprehension at scale with the repository data that we have. And this is what repositories are great at. They offer longitudinal, ecologically valid ground truths in which to test hypotheses about comprehension. And in fact, some of the papers that I saw in the proceedings for ICPC are doing this already. 10 of the preprints actually used repositories. They just haven't used them for program comprehension studies yet. So how do we get all of this strong evidence? Well, there are repositories that hold traces of developers' comprehension of code. We just haven't really thought about how to measure that yet. So for example, defects might indicate some failure to comprehend. There's a relationship there that we can exploit. Communication may indicate comprehension needs, right? So the need for people to talk might indicate that they need some knowledge they don't have. Complexity might suggest comprehension barriers, right? So the complexity of a component might impose some difficulty in comprehension, and we can understand those relationships more deeply. There aren't that many studies that I've seen that actually try to model these indicators of comprehension. So here's an example of how we might do this. I'll start with a theory. Hidden semantics result in developers with brittle comprehension of API semantics, who then write brittle code. So this is the idea that if you don't understand how a function is going to execute in an API, you're going to not use it in a robust way, and that'll result in defects. An example of this that I've seen in practice is that many users of the Facebook React framework don't understand which calls are asynchronous and which ones aren't. And this leads to some code that seems correct if you test shallowly, but if you test in production, it actually fails. So I have a hypothesis based on this theory that the more hidden the API semantics, the more defects you'll see. And we can actually test this with repositories. For example, we can measure how hidden semantic facts are, how hidden facts are by counting the number of Stack Overflow questions about that API. That's an indicator of how much it is that people are struggling to learn these facts. And then we can measure the defect density of components, correlate, and we would expect based on this theory that there's a strong correlation. So that's just one example of how we might more deeply investigate theories of program comprehension with large data sets. In fact, some studies from Mining Software Repositories are already doing this. There's this great study at MSR called Prevalence of Confusing Code in Software Projects, Atoms of Confusion in the Wild. And it actually operationalizes an indicator of comprehension and shows a correlation between confusing patterns and bug fix commits. So this is a great example of one of these opportunities for fusing together comprehension and mining. Now, the impact of doing some of this mining the mind is more longitudinal, community-wide measurements of program comprehension in ways that lab studies just can't give us. There's opportunities for descriptive and predictive models of a community or an organization's comprehension gaps. What would it mean to understand an entire team's inability to understand some part of an implementation? And we can also develop associations between comprehension and defects and productivity and other outcomes that we care about. So all of this is really leveraging that same opportunity that MSR has always been leveraging of using these large data sets to answer questions we couldn't answer before. So comprehension can leverage mining's methods, but mining can leverage comprehension's methods too. And so here, I'm calling this minding the mind, thinking about a developer and their experience in the context of how we're mining repositories. So here's the problem I see with MSR studies. Many papers do a great job testing certain outcomes, things like feasibility, correctness, coverage, and accuracy of predictions. But when I looked at 11 preprints at MSR 18 that evaluated tools intended for developers, only one actually evaluated the usefulness of the tool with a developer. Everything else was about feasibility. This bias towards this overall assessment of applicability of a tool overlooks really critical questions about how these tools would be used by developers and managers and teams to actually improve software engineering. It's this disconnect from practice that's highly problematic. And it leaves a lot of really fundamental premises about the utility of mining tools untested. I'm going to pick on a paper now, so warning. This paper, Analyzing Requirements and Traceability Information to Improve Bug Localization. It's a really clever use of previously fixed bug reports to improve localization. And it really had a really large scale evaluation against 13,000 bug reports. But there was no evaluation of whether a ranked list of source files is actually useful to developers in comprehending, localizing, or repairing defects. It's just sort of taken as given that this would be useful output to a developer. Really, the solution here for problems like this is that we have to test these unverified premises with real developers on real teams. And this is something that studies and researchers in program comprehension have done for quite some time. Here are some premises that really need to be tested, but I don't know of any evidence that have been tested. Managers want to analyze their team's activity. Do they? I'm not sure. I certainly didn't. I wanted to talk to my team. I didn't want to sort of analyze them through data when I was at my startup. Predictions are trusted and actionable. I rarely found this to be true. It seemed more often that they were not to be trusted and they were not actionable. And most tools that offered predictions were actually not that useful in practice. Patterns in source code lead to valuable insights. I didn't ever find a tool that provided me useful patterns or useful insights. Maybe some of the research tools do, maybe they don't. How about another premise of patterns in communication lead to valuable insights, right? Studying how it is that people are talking to each other is useful. I don't know that this is actually true either. When are they true? When are they not true? Why would they be true? And in what settings? So the approach here that comes from program comprehension that should be used in mining is put tools in front of real developers and real managers and real teams. Show them our vision of how mining tools can be used to impact software engineering practice, elicit their questions, their concerns, their ideas, get feedback on the actual use and utility of the tool. And better yet, try to deploy mining tools into practice and evaluate how they don't and do support software engineering in practice. Here's an example of a kind of study that we might do. Let's look at prediction, for example, and its actionability. A lot of research in decision sciences shows that people generally don't use data to make decisions. They use data to confirm prior beliefs. That kind of destroys the premise of predictions being valuable. But let's test this hypothesis that developers and managers will view fault localization predictions as evidence of their prior knowledge about components and see little actionable insight. There's my prediction. So the method here, let's just recruit 30 open source developers, present some fault localization source file rankings on their system that they're familiar with, and then challenge them to extract some novel actionable insights from the data. It's a pretty simple design, doesn't require that much preparation, really just sort of some recruitment, and we can test this hypothesis. Somebody should find out. So if we do this, we might learn, for example, that many mining tools make predictions that will be viewed as useless by developers. We might need to reconsider what output would be valuable to developers and managers and think about completely different architectures and functions for the types of predictions we make, or question the value of predictions at all. And we might need to invent new algorithms and tools to achieve some kind of utility around these things, right? We might need tools that explain instead of predict. In fact, some studies in ICPC are already doing studies like this. And in fact, the one that we talked about, the JIT feedback paper that we just discussed, does a great job of trying to understand developers' perception of value of tools output. And it provided really rich insights about precisely which rules in these static analysis tools were valuable and which rules were not and why. It started to help develop some explanation about when a static analysis tool would be valuable. I recognize that running studies with human subjects is hard. I received a lot of requests over the years to try to help share some knowledge about how to do this. So my collaborators, Thomas Latoza and Margaret Burnett, and I wrote down many of these things for you in this Empirical Software Engineering Journal article called A Practical Guide to Controlled Experiments of Software Engineering Tools. What it actually is a big argument for why you should not run controlled experiments and instead try to focus on getting more formative data. But if you really must, it'll give you all of the information that you need for how to do that. Now, if we do some of these studies, we can have a lot of impact. We can show that our tools are actually useful. We might develop some new science of software analytics decisions and how developers and managers make them. We might find new tool requirements that require further research by trying to understand the limitations of our designs now. And we might actually just have more impact on practice by focusing on what the actual impact of the tools are. All right, so I said mining should involve more people and comprehension should involve more mining. These are pretty obvious ways of bridging these two disciplines. But there's one thing we're still missing, or one really big thing, and that is theory. I gave some examples in previous sections about some informal theories to try to explain some phenomena, but I want to give some more detailed explanations here. So here's the problem. Most program comprehension studies describe or predict behaviors, practices, strategies, effective tools, but very, very few that I've seen try to explain any of the phenomena that they see. Most mining studies describe or predict patterns, associations, and trends in various aspects of repositories, but again, very, very few try to explain the patterns that they see. I went ahead and looked at all the preprints for ICPC and MSR this year, and none of them had formal or informal theories that informed tool design or empirical study design or the interpretation of any of the results that were observed. They were purely describing or predicting and not explaining. The problem here is that without explanations, all we have is some loosely connected set of empirical patterns with no greater theory of how they relate. We really have to generate that theory to build upon each other's discoveries. So let's talk about why this is necessary. We have to produce theories that explain the major phenomena in software engineering, comprehension, process, coordination, defects. And we have to explain why defects occur, why builds fail, why decisions are poor, why projects are late. By generating these explanations, we can derive hypotheses and test them in the lab and the field with developers and with data. Theories will help us combine our results and communicate greater truths to industry about software and software engineering. None of this should be surprising. This is just basic science 101, right? Generating theory. And yet, because of our interest in computer science about generating new technologies, I think we've sort of been ignorant of the fact that most of our discoveries and our research really aren't impacting our basic understanding of what software engineering is as an enterprise. So let me give a couple of examples of theories that exist and how they're being used to advance software engineering and why I think they'd be valuable in comprehension and in mining. So example number one is Jim Herbsleb's socio-technical theory of coordination. Jim's been working on this for a while, but he gave some keynotes on it recently that I explain it well. And he basically is presenting a theory here of how teams coordinate work. He's arguing basically two things: that software is an interdependent network of decision constraints that are imposed by technical dependencies, and that things like teams and process and modularity, all of these are efforts to align coordination requirements determined by these constraints with the coordination of individuals. And all of that is basically some fancy language for this much simpler explanation, which is that if developer A owns function foo and developer B owns function bar, and foo calls bar, then A and B have to talk to each other. They have to talk to each other about foo and bar, and they have to coordinate the relationship between those two functions. And so these technical dependencies result in social dependencies. So this is an example of a great theory from software engineering research that can explain a lot of the things that we see in studies that mine software repositories. And there's a lot of good evidence for this too. So the theory predicts, for example, that misalignment between social and technical constraints will cause defects and delays by limiting the information that developers have for decision making. And there's several studies that Jim and his former students have done that show that these are true. Misalignment is related to time to resolve modification requests, and misalignment explains increases in software failures over time. This is the kind of theory that we should be building on. So everybody in the room should be investigating questions of coordination with this theory, attempting to falsify it, right? That's what we do in science, is we say that this is how something works, and then we all try to prove each other wrong. We should be using the theory to interpret prior work in mining software repositories and comprehension, to derive hypotheses, to test them, to interpret results, to connect these results to prior work. All of this will allow us to integrate our individual publications into a greater whole, explaining the work of software engineering. I want to give one more example of a theory. This one's not on coordination, but on defects. And it comes from Donald Knuth, of all people. So back in 1989, Knuth wrote a great epic qualitative empirical study called The Errors of Tech. I don't think he knew it was qualitative, but that's what it was. It was a 10-year diary study of defects. And inside it is this really fascinating theory of how defects arise in practice. And so I took this and combined it with a bunch of other research in human error from human factors research, and mapped them onto all of that work in human factors into a theory of defects in this paper called A Framework and Methodology for Studying Causes of Software Errors in Programming Systems. And it boils down to these 5 sources of all defects in software. Number 1, failure to attend closely to a routine action, like choosing an item in code completion, but not paying attention to which one you chose and choosing the wrong one. Number 2, misapplication of a rule in a novel context. So this might be something like using a for loop increment template for a problem that required a decrement. 3, using a bad rule, so a rule you should just never use. For example, using for loops instead of iterators, because for loops are less safe and can result in more defects. Source number 4, incomplete information about a problem space. So like this would be an example of brittle knowledge of an API's expressiveness would make it hard for somebody to find the right solution to a problem. And then source of defect number 5 is that the problem space is just too large to comprehend. An example of this would be reasoning about human behavior in a driverless car context. It's hard to write programs that do this, and so we're just going to produce defects in the process. We can test this theory and find out whether these 5 sources are actually true sources of defects. So here's an example. Let's take the theory that it's failure to attend closely to routine action that causes defects. Well, here's one hypothesis we can derive from that. Developers read and write a lot of routine for loops, but when those for loops deviate from routine, we should see that developers will overlook this deviation, and this will lead to defects when they modify things related to that for loop. How might we do this? We could measure the defect density of functions and then the deviancy of those for loops from convention, and then correlate just to see if those are related to each other. And that would be more support for our theory. If we test this hypothesis, we start building a grand theory of where defects come from, one study at a time, we can start to explain the results of all of the mining studies that we have and all the program comprehension studies that we have and unify them together into one coherent body of knowledge. Now, if we spent all this time developing and testing theory, we may produce a grand theory of where defects come from. We could use it to reliably predict when defects will occur and help to prevent defects from occurring by training developers more to be mindful of all of these sources. We could design processes around them as well. Right now, all of this theory is sort of implicit in our understanding. It's all folk knowledge rather than something explicit that we actually develop rigorously and scientifically. Theory isn't just for tools. Theory is actually for tools as well. It's not just for empirical studies. Tools embody theories of programming. For example, the implicit theory of defect prediction tools is that developers and teams need help localizing defects and prioritizing testing. We don't know if this theory is true, so when you design a tool, try to make your theory explicit. So really, this is a theoretical call to action. I think that all research on comprehension and mining, empirical or technical, should advance or falsify theory about software engineering. If we all do this, then we can have a common framework in which to combine our individual discoveries into greater truths. All right, so we've talked about 3 missed opportunities so far: applying mining to comprehension, applying comprehension to mining, and using theory to explain mining and comprehension and unify the results that we get from them. So in this last part of my talk, I want to talk about some of the grander challenges I think our community should be tackling. And I want to start with this study from a couple of years ago from Microsoft Research that showed that according to at least 512 practitioners at Microsoft, about a third of our research ideas in software engineering are not considered actionable, useful, or generalizable, or they're considered too costly. And that there's really no correlation between what developers valued and what we cite in research. This is a big problem. This tells us basically that the work that we're doing just is not relevant. It's not something that most developers view as valuable. And what we should be doing here is really focusing on the big questions that industry can't answer. I presented a paper last year at ICPC's Software Engineering in Practice track about my experiences in industry. And here are some of the questions that when I talk to CTOs as a fellow CTO about research, these are the ones that they asked me. How can I know a new software process will help if I adopt it? How can I onboard new developers faster? How can my developers learn APIs faster? How can I align my technical decisions with my business priorities? How do I know what's happening in the field if nobody reports it? How can I discover single points of failure, not just in my infrastructure, but in my processes and my developers? These are the kinds of questions that they wanted answers to, and really research provided no answers to any of them. And we can answer these, right, with comprehension and mining. But we also need other things. We need organizational scientists, we need management scientists, we need learning scientists, because all of these questions concern organizations, management, and learning. We should be bringing together interdisciplinary teams to answer these big questions. So here's an example of one phenomenon we could be studying together. Onboarding. Millions of developers start new jobs every year, but aren't productive for months because of the complexity of the systems that they're trying to contribute to. How do we help them onboard faster? Well, we have a couple of studies of onboarding that suggest that organizational management theories of newcomer socialization best explain what onboarders need. And then they talk about specific things that might help, like mentors, models for proper behavior, connections to expertise about architecture, code review practices, norms about meetings, walkthroughs of feature implementation, and lots of other ideas. One idea here was these walkthroughs of feature interviews in which a new hire meets with a developer to learn about the feature the developer owns, the architecture of the features, and how the features are situated in the larger architecture. We could be supporting these through entirely new classes of architectural walkthrough tools that situate features in architectures and provide rationale and reveal business goals and surface practices and norms around process. And there's a lot of interesting questions here about each of our respective fields and how they might support this really relevant task. For example, how can comprehension help? Well, try to answer these questions. How can developers author a walkthrough to reveal this information in a future interview? How can we know if an authored walkthrough will produce an effective comprehension of an architecture? What data other than code would be necessary to surface in a walkthrough? These are really foundational questions about program comprehension that go well beyond reading code, and we really need to be answering them to be relevant to industry. Well, how can mining help this same problem? Try answering these questions. What kinds of project history are necessary for comprehending architectural rationale? Right? We need this data to be able to comprehend it. What is that data that's needed? Can we help a developer prepare for a walkthrough, predict what code is necessary to discuss? So there's an opportunity to use prediction. How can we use contribution history to recommend who's qualified to author a feature walkthrough? These are, again, foundational questions about prediction and mining that go beyond just understanding repositories and defects and really go to understanding how to support somebody entering an organization to build software. All of this is very atypical software engineering research. It requires us to tackle phenomena we don't usually study, like organizations, learning, teaching, business decisions. It forces us to tackle real struggles that industry has. And it requires interdisciplinary expertise to do it. It tackles research contributions that may not look like the technical and empirical contributions we typically value in software engineering research. So that requires us to change what we actually value. And the result of it is that we might advance theories of organizational learning, design in HCI, and strategies in computing education. And all of that's okay. There was a time when software engineering research really rejected empiricism of any kind. We can move to a place where we actually value these kinds of highly relevant problems that synthesize many different perspectives. So mining can increase comprehension scale. Comprehension can increase mining's impact. We need theory for progress and unification, and we need to be asking more relevant questions. So how do we achieve this? Well, here's a couple of things of advice from a person who does a lot of interdisciplinary work. First, you have to make time. To aim this high, to be relevant, and to do this kind of interdisciplinary work, we have to think more about the next paper or promotion. Some of these problems might take multiple years before we have progress worth reporting. If you have nothing to say at the next ICSI because you're still working on it, that's okay. If you have tenure, like I do, use it to think bigger and broader and longer. Try to solve bigger problems and leverage that protection that you have. Second, be inclusive. Technical contributions matter. They matter to me, they matter to our field, obviously. But to make progress on a lot of these big relevant problems in industry, we have to value other forms of scholarship. Theory, development of instruments, empirical studies, all of these things are necessary for progress, not just invention of new tools. Third, we have to read other disciplines. HCI, organizational science, management science, cognitive psychology, social psychology, all of these other disciplines are explaining the software engineering phenomena that our field is investigating. We should know what they've discovered and build upon it and not pretend that it doesn't exist. Number 4, connect with software engineers and CTOs. Visit local meetups, talk to them about what's hard about their jobs, discover what questions they have. Just learn from them about what's happening in practice. You'll be surprised at how little their needs actually align with the questions that we ask in this community. And finally, connect these two communities, connect mining and program comprehension. I think you have more in common than you think, and you can use this week to find out what that common ground is and maybe even find shared projects in some of these spaces. The cost of not doing any of these things is actually quite high. If we don't pursue interdisciplinary work, I think our field actually may become irrelevant. We have to show the world that the questions we answer in software engineering research matter not only to computer science, but they actually matter to software engineering practice. We have to show relevance not only to that, but to fields struggling with software development. These days, medicine, natural sciences, public policy, law, all of these fields are building software, and we have nothing to tell them at this point, other than lots of stories about how formal methods will make all of their software better. We need to put our attention on these other disciplines, not just safety critical domains. Now, if we do this, I think our work will be more deep and it'll be more impactful. So I hope you all join me in learning to do interdisciplinary work. Thanks for your attention, and I'd be happy to take your questions.